Welcome to the course Excelling with Mathematical Modeling. Today we will be learning about the growth models. So, to start with, we need to know how the interaction happens. So, it happens due to the law of mass action. This law of mass action in chemistry, it states that the rate of a chemical reaction is proportional to the product of the concentration of each reactant. Now, this idea was interpreted in mathematical biology by the American physical chemist Lotka and Italian mathematician Volterra. So, this is Lotka and this is Volterra. So, they propose that if you have a prey-predator model and there is an interaction between the prey and the predator, so that should be treated like the particle interacting in a homogeneously mixed gas or liquid, and under these conditions the rate of encounter between the prey and the predator should be proportional to the product of their masses. Meaning is that if you have a prey and a predator, so this is a predator, a snake, and this is a prey, the frog. So, when there is an interaction between the predator and the prey, in this case the snake and the frog, and if you denote them by say x and y, so they should be treated as the product of x and y. So, that is what the use of law of mass action in this modeling. So, whenever there will be an interaction between two species, it will be treated, it will be taken as the product of the two variables. Now, Crawford Stanley Holling is a Canadian ecologist. He introduced the term called functional response. Basically, it is introduced to describe the change in the rate of consumption of prey by a predator when the density of prey is varied. So, the two types of function which we will be discussing here is Holling type 1 and Holling type 2. So, if you have a prey and a predator and the interaction is happening at a rate say beta. So, this is a Holling type 1 function where these two appear linearly as a product, say this is the prey and this is the predator. If we look into Holling type 2, the function will be of the form say beta x by x plus k times y. Now, we generally take this kind of function when this predator does not have access to the whole of the prey. It has access only to the fraction of the prey. For example, say if I take this x by x plus k, this I can write as 1 minus k by x plus k. So, if you simplify this, you are going to get this one. So, as you can see that it is a fraction of the prey that is accessible to the predator if I multiply it by y. So, whenever a situation arises when the predator does not have, or when one species does have access to the fraction of the other species, we generally use this Holling type 2 functional response. And in most of the real life cases, it has been seen that this functional response is more close to the real life scenario than the Holling type 1. But again, in mathematical modeling, we use simple functions, and if the simple function is able to capture the dynamics of the model, we are quite happy about it. We now come to our main topic, the growth models. So, to start with, we have the linear growth model. Now, in linear growth model, we assume that the growth of the population is constant. So, if x is the population, the rate of change of growth is a constant. And it is a simple differential equation. If we just solve it, we will get x equal to kt plus some arbitrary constant c. So, if we plot this graph, as you can see, this is of the form y equal to mx plus c, which is a straight line where m is the slope and c is the y intercept. So, if you plot the graph, you will get a straight line where this is your c, assuming that c is a positive, and this is x equal to kt plus c. So, this is a linear growth model. We next move to exponential growth model. So, in exponential growth model, you consider, say, a population with plenty of resources. And there is no threat from anybody, say any predator. So, in such case, the growth rate is proportional to the population. So, that means if x is some species, then dx dt, the rate of change of the population, it grows, it is proportional to the population, which is x, and this will imply dx dt equal to some r times x. Now, if you simply solve this differential equation, you will get this, and this will imply log x equal to RT plus integrating constant. So, ln x means the base is e. So, if we take the initial condition, say at t equal to 0, your population is x 0, this will imply constant equal to x 0. If you substitute it there, sorry, constant is log of x 0. If you substitute it here, you will get ln x equal to RT plus log of x 0. So, and this implies x equal to x 0 e to the power RT. When you write this ln, you do not have to write e, but just for the sake of understanding. So, this is the solution, and if we plot this solution, we are going to get curves like this. However, as you can see that this is sort of unbounded, because as if your r is a positive number and as t increases, your x also increases. But generally, we do not take this kind of assumption unless needed, because the growth, if it is unbounded and growth unlimited, it really does not capture the real life scenario. So, that is why it is the start that there is something called exponential growth model, and unless the model demands, we generally avoid this exponential growth model and move for the more realistic one, which is a logistic growth model. So, in logistic growth model, we have the equation of the form dx dt equal to r times x 1 minus x by k. Now, this r is called the intrinsic growth rate, and K is called the carrying capacity. Now, the growth rate you can understand, the intrinsic growth rate. We use the word intrinsic because this contains birth rate minus the death rate. So, both of them are contained in this, and the carrying capacity can be understood like this. You consider somebody is having a tumor, say in the liver, and it is growing. So, generally if it grows, it will first start like this, but after some point it will go like this. That is in general what happens in a growth model. So, there is some sort of exponential growth, and then it ceases to grow and then comes to a constant value kind of thing. So, this carrying capacity is something which your environment can support. For example, you consider this tumor and it is growing in the liver. So, how much that body can support or can provide support to that tumor so that it can grow substantially. So, that is what is called the carrying capacity. We will take this carrying capacity again when we come to this prey predator model, but something that your environment can support to grow. In this particular example, suppose if your tumor is growing and it ceases and comes to a constant value which is k. So, beyond k it will not grow. Okay. So, that is what your carrying capacity is. Now, if we try to solve this, this can be easily solved. You separate the variables. This is R x k minus x by k, and this you can write as x into x minus k equal to some minus r dt. You integrate. This is a partial fraction. I can write like this. So, if I simplify this, I will straight away get away this. So, I think I miss x. So, there is a 1 by k. So, and if we take the initial condition that at t equal to 0, x equal to x0, we substitute this value and we can calculate our solution in the form xt equal to k x0 divided by x0 plus k minus x0 e to the power minus rt. So, I leave it to you how to find this solution. It is just integration, you get this result, substitute at t equal to 0, x equal to x0, and simplify, you will get this result. So, from here you can see that as your t becomes large, this part goes to 0 and your xt will go to k x0 by x0, this cancels, so it will go to k. So, for large t, as this graph suggests, your value will reach the carrying capacity k. So, this is the logistic growth model. In most of the modeling where we involve this growth, we use this logistic growth, which is more realistic than the constant growth rate. We have a second function which also represents growth, and that is called Gompetz growth model or Gompetzian growth. In this case, your equation takes the form Rx ln k by x, where your R remains the same, it is the intrinsic growth rate, and K is the carrying capacity. Now, again we find the solution of this growth model. This can be written as x ln k by x equal to R dt, separation of variables. We write this as d of ln x with this, and this can be written as ln x minus ln k with a negative sign, and I take that negative sign to this side. Okay, if you are not familiar with this equal to this, you can keep this whole x like this and then substitute this equal to z. You are going to get the same thing. Or otherwise, d of ln x is just you write the differential of this, that is 1 by x and dx. So, you get this part. Or otherwise, you can do like this, you can just write this as integration dx by x, then ln x minus ln k with a negative sign, it will go to minus r dt, and then substitute z equal to ln x minus ln k, your dz is going to be 1 by x dx. So, that is how you do the substitution. So, this will imply ln of ln x minus ln k equal to minus RT plus constant, which implies ln of ln x by k equal to minus RT plus constant. At time t equal to 0, you take x equal to x0, substitute it here, and this will give you constant equal to ln x0 by k. So, if you substitute it here and take it to the left hand side, you will be getting ln into ln x by k divided by ln x0 by k equal to minus RT. So, ln x by k is equal to ln x0 by k into e to the power minus RT, and then x equal to k times again the exponential exp of ln x0 by k e to the power minus RT. Again, in this case, you can see that as t becomes large, then this part goes to 0. So, it is exponential 0, which is 1, and you are left with x tends to k. So, a similar kind of behavior, and in most of the cases we use either this logistic growth expression or the Gompetzian growth. Now, let us see what is the numerical solution provides you what kind of graph, both the case of logistic and the Gompetzian growth. So, we will be using Microsoft Excel to find the numerical solution of these two problems. So, as you can see, I have already have the equation typed. So, this is the logistic growth, it is Rx1 minus x by k. This is the Gompetzian growth, Rx log of k by x. The initial value for both of them I have taken to be 5, R is 0.8 and carrying capacity k is 10. So, I will use this formula which we have done before, that y1 is equal to y0 plus h times f of x0 y0. So, if I come here, so to calculate this x values, what we do is this is equal to x0, which is this value, plus h we took as 0.1 multiplied by, and since h is constant, we put a dollar, multiplied by x0, which is multiplied by 1 minus x0 by k. And since k is constant, I put a dollar and enter. So I calculate these values up to 50 of them and I get this. So if I want to plot this, I will come up to here, I go to insert, go to scatter and I plot this. So I get something like this. The same I can do with the Gompetzian one. So I will take here, this is equal to, I have the same x0, which is this, or I put this one as x0 plus h times, which is a constant, times this is your r, which is again a constant, r times x, sorry, r times x, and then multiplied by log. So here it is log, here it is log 10. So you will use log, which is log to the base e, log of k, which is 10, and it is a constant, divided by x0. And I drag this. So if I want to plot this again, I go to insert, I go to scatter, and I click this. So you have another graph. So numerically, if you solve them, you will get these two graphs. So we have solved these two numerically using Microsoft Excel. Let's now compare. So the values, as you can see, I put the initial value to be 5, the intrinsic growth rate to be 0.8, and the carrying capacity to be 10. So both of them have started from the value 5, and this is what the graph looks like in case of logistic growth, in case of Gompetzian growth. Now if I compare both the graphs, as you can see that both have started from this 5, the logistic growth is a bit higher than the Gompetzian growth with the same set of intrinsic growth rate and carrying capacity and initial value. So the question is which one to use and which one is better than in a particular model. So it goes like this, that when you model something, say whether it is a growth of a population or whether it is a growth of a tumor, you will be going to get some data. and from that data you have to choose a particular function. So, in some data you will see that this logistic growth function, which is of the form Rx into 1 minus x by k, this fits well than the Gompetzian function, which is Rx ln k by x. So, that way we choose that which growth function will be better for a particular model, whether will be a logistic growth or whether it is a Gompetzian growth. Both depends on the kind of data which you get from the real life scenario. So, with this we come to the end of this growth models. In the next lecture, we will be learning about the pre-predator models. Till then, bye bye.